In this video, we're going to learn how to sketch exponential growth and decay, and we're also going to solve some questions accordingly. First things first, let's jump into Desmos to get an understanding of exponential graphs themselves. Here we have a graph of y equals 2 to the power of x, and we can see that it grows really fast. A useful way to analyze the shape of this function is to understand the nature of indices. We know that as x grows larger, the value of y will double over and over again, causing a large spike in the values for y. We can also see in this graph that the value for y will always be positive. Okay, it shoots off towards y equals 0 as x gets negative. Again, it's useful to think of this function by understanding the nature of indices. As x goes towards a large negative number, the value of y will be fractional. This creates an asymptote at y equals 0. Okay, we will never get y equals 0, but as x gets larger and larger negatively, the fraction just gets smaller and smaller and smaller. We can play around with this function by just adding or subtracting a constant value. Here, if we just added 5, we can see that shifts the asymptote up. And if we subtract 5, we can see that shifts the asymptote down. Now, what we notice is if we shift the asymptote down, we have got two intercept points. We've got an x-intercept and a y-intercept. Okay, that is useful to remember when you're dealing with the algebra of sketching exponential functions. So the y-intercept can be shifted up and down by playing around with a constant value inside the power. So if we took this power and we went plus, well, initially the y-intercept occurs at the point 1, and that's because when x is equal to 0, the corresponding y value will be equal to 1. Again, think of the index laws. 2 to the power of 0 is equal to 1. If we add a constant value, so if we add 1 in that power, we can see that it shifts the y-intercept up to the point 2. And this is because the y-intercept occurs when x is equal to 0. So when x is equal to 0, this is just going to be 2 to the power of 1, which is 2. And then if you add 2, you get a y-intercept of 4. And this y-intercept will grow exponentially. So if you went plus 3, you get it to the y-intercept plus 8. If you went to 4, you get the y-intercept to 16. And that's because the y-intercept occurs when x is equal to 0. So there's those transformations to remember as well. As usual with any function, we can play around with dilation by just multiplying by a number. So if we multiplied 2 by 3, okay, we can see that makes the graph shoot up faster. And we can also make it shoot up faster by changing the base number from 2 to something like 12. Okay, and if I zoom out here, you'll be able to see this very clearly. Okay, and we can also have reflections of this as exponential growth. We can reflect it over the x-axis if we just take the negative of the entire function. So that is a reflection of exponential growth. You're just taking all of the negative values. Okay, so that is for exponential growth. What if we consider exponential decay? Well, exponential decay occurs when we've got a negative of the power of x. So we can see here that we've got exponential decay when we take the negative of the power. Alternatively, what we can do is we can change the base number to be a fraction. Okay, in this case, a half. Right? But that is actually the equivalent of just taking the negative power. So y equals a half to the power of x is the same thing as y equals 2 to the power of x. So we can see that green line directly overlaps that red line, and there will be an example on the screen as to why that is the case. A useful way to analyze the shape of exponential decay is to again think of the nature of indices. This is just y equals 2 to the power of negative x. So you're just negating whatever the x value is going in. So if x is negative 4, that's like saying y equals 2 to the power of 4, because the negatives will cancel each other off, and you'll get a value of 16. And we can see that up here, right there. Okay, if you took x being 2. Okay, that's y equals 2 to the power of negative 2, which we know would be a quarter, and that would be right down about there, at a quarter, right there.
So now with that stuff out of the way, what we're going to have a look at is the general form of an exponential. Okay, here we've got the dilation factors, horizontal shift, and vertical shift. Okay, and we know how they manipulate the function on the Cartesian plane. The next thing that's useful to know is how to sketch exponential functions. Okay, I've got a 5-step kind of guide to do this. Okay, first one, find the asymptote. First thing you do. Second thing is you find the intercepts if they exist. Third thing, you consider the shape. Okay, that's going to help you draw the long-term behavior of the exponential. Find a second point, okay, because you need to connect the dots if you don't have 2 intercept points, and then we scale and label it, putting it onto the graph accordingly. So first example here, we've just got sketch this exponential y equals 4 to the power of x plus 1 minus 2. Okay, just starting off, I'm going to follow my 5-step procedure. First one is the asymptotes. Okay, so what I need to do is I just need to state what the last variable is, okay, that constant variable, and I know that that is going to be an asymptote. Right. The second thing that I need to do is find my intercept points if they exist. Okay. Now remember, since we have got some exponential growth occurring here and the asymptote has been shifted down, if you can visualize this, we're going to have 2 intercept points. That is nice. Okay, so finding our x-intercept, we get x is equal to negative a half. We're going to do the same thing for the y-intercept. Okay, so then we have got our x and y-intercepts. Okay, and to name them a little bit more explicitly, that means we've got 0, 2 as a point and negative a half, 0 as a point. Okay, they're just our intercept points. I've got asymptotes and intercepts. Okay, the third thing we wanted to consider was the shape. Okay, so this is 1, this is 2, this is 3. The shape of this, we need to consider whether it's reflected or whether it grows and decays. Okay, so we can see here, well, how I would write it is I've got A being greater than 0, therefore no reflection. And I also know that I've got growth, so that's when B is greater than 0, therefore growth. And so what that indicates to me is if I was to draw it, okay, this is just going to help you visualize it. You've got exponential growth and it's not reflected over the x-axis. So it's just going to shoot up like that. So that's going to be the behavior of it. It goes up this way and then it asymptotes off. Okay, at least in this case, we've actually got an asymptote down, so it's going to look more like that. Okay, because we've got that horizontal shifting down. The fourth thing we would have needed to do was find a second point, but here we've already got 2 points, so we don't need to do that fourth step for this case here. And then all we need to do now is we just need to scale and label an axis and draw it on. Okay, and so when I go to sketch it on, I know I'm going to have, so I like to put it in order. So the first thing I found was an asymptote, so that's the first thing I'm going to put on, and then I'm going to put on my intercept points. Okay, that is when I am at the point 0, 2, and negative a half. And I know the shape of this. Okay, what's happening is it's going to shoot up like that, and it's coming down through here, and we'll asymptote off there. Okay, that would be the sketch. Okay, moving on to an example that is a little bit trickier. So first off is the asymptotes. Okay, so I get a y-intercept of 7/4. I go ahead and I try and find an x-intercept. Okay, now he was stuck. we're stuck, there's no x-intercepts, and it should be a giveaway as to y. Okay, here we have got 3 times, okay, we can kind of just ignore that 3 times. We've got 3 lots of something raised to a power. Something raised to a power is always positive. Even if you have got the most negative power, it is still positively fractional. So we cannot get a negative answer. So we're stuck, no x-intercepts. That means for this case, we are going to need to find a second point. Right, we can consider the shape of this exponential. Okay, we know here that we've got a being positive, therefore no reflection. But what we have got is we've got b is negative, therefore we've got decay. Okay, that power is negative. So we have got exponential decay, which means that it's going to look like this. Okay, and asymptotes off at y equals 1. And so that's why we've only got this one intercept there, which is at 7/4. Okay, what we're going to need to do is we need to find ourselves a second point. So the way that we do that is, well, my simple instruction is I'm going to consider it when the power is equal to 0, because that's when it's easy to solve. Okay, so that means that's the point x being equal to -1. Okay, and we probably already could have seen that. So that means that we're going to take the point x equals -1 and find what that corresponding y point is. Just so we've got a second point so we can do a dot to dot, more or less, when we're putting our exponential together. And so the way that we've structured this is we're not going to write in 2 to the power of negative and then substitute in when x is -1. We know this power is going to be 0. We know this power is going to be 0. Okay, that's why we wrote it. Plus 1. So that means we've got y equals 3 times 1 plus 1. So we get y equals 4. So this gives us our second point at -1, 4. Okay, which if we kind of refer back up here, that's going to be like something like that. Okay, now what we need to do is we just need to piece it all together, which is step number 5, scale it and label it on a Cartesian plane. Okay, and so that is our sketch fully put together.